Welcome to week 3. So in this particular chapter, we're going to cover how some basic techniques on how to fit models to data graphically and some analytic methods for model fitting and applying the least squares criteria on selecting the best model. Least squares is one of the very important concepts in math model, especially in regression. We're going to talk about this in this chapter. So there are 3 tasks when we are analyzing a collection of data points. Fitting a selected model type or types of data. The precise meaning of a best model must be identified. So, and also choosing the best, most appropriate model from competing types that have been fitted, and making predictions from the selected data. So it's almost like fitting the model, select the best model, and then make the prediction based on the best model. However, in a modeling process, it always have some sort of error. And sources of error could be from formulation, could be from truncation, could be from runoff or measurement. Formulation is essentially the math modeling piece. We hope that the model itself is not wrong, although we could face a situation that the data may not be perfect, but we hope the model itself is solid so that we can make valid conclusions. So we need to visual fitting could have potential pitfalls. We might need data transformation for fitting the data graphically. And here, for the example in the textbook, in the figure 3.12 and follow us example, the example are actually later on modeled as a minimization problem, and it's a linear optimization problem. And we would try to solve the problem in chapter 7, try to use the simplex method, will be explained later very carefully in chapter 7. And least square criteria is sum of squares of the error. So in trying to fit in a strict line, we try one very important concept is how are we going to measure how good the model is. So there you go. We use least squared error, meaning the difference between the observation and the fitted value squared, sum of that squared, which is that's why it's called the least squares criteria. Formulate this is a steps for how to fit a straight line. Formulate the least squares, take partial derivatives, and then set partial derivatives to 0. Solve for slopes and intercept. And it could be a power curve or transform linear squares fit. So that's beyond linear regression. Could be nonlinear, could be transformation from nonlinear to linear. These are covered in section 3.3. Please read the textbook. Ask questions if you have any. And also how to choose the best model. Fitting error, comparing the models, and the considerations that in choosing the best model, you can look at the error, you can look at how complex the model is. Sometimes maybe we don't really need a complex model if it's just too difficult to collect the new data set for prediction purpose. Pay attention to overfitting. Overfitting is a very important example. is a very important concept in modeling. Overfitting meaning that you fit the data too well, which makes it's impossible for you to extrapolate beyond the data itself. And the generalization of the model, would you be able to generalize the model and apply it to a new data set? These are the homework for chapter 3. Try to deliver the homework by the end of Sunday. Thank you. For week 3, we have another topic: experimental modeling. It's majority of this chapter actually were explained by some very nice examples. So here, see, look at the data. If the model assumption lead to an expectation of a quadratic model, it could be this. Parabola will fit the data points, or a smooth curve would work. So those two would be different. And later we probably need to look at which actually have a better fit. Earlier we discussed regression. We could apply similar error term. We could apply similar techniques for quadratic or a higher order model as well. So sometimes we have to transform the original data. Here is a ladder of the transformation. So we can start from the original data z squared, z log z, so on and so forth. After the transformation of the data, it could be the case that the problem becomes more tractable. And here is some examples of the relative effects of 3 different transformations. So if y values are replaced by square root of y, it's no longer a linear model. Or y values are replaced by log y, or y values replaced by 1 over y. Okay, here is a Lagrange form of the polynomial. So we talked about this earlier, potential problems of high-order polynomials. So we have to consider the error, consider the complexity of the model, consider whether it could overfit the data, and how generalizable the model is. And for lower order polynomials, the error can be worse, but the complexity of the model decreased, overfitting of possibility decreased, generalization of the model increased. Here, linear splines are called piecewise linear. So essentially meaning pieces of linear combined together would be the whole model. Or we could fit the model as cubic splines. So here are the homework for chapter 4. Thank you.